Hi, my name is Brendan.
Hi, my name is Nur Ada Sabrina.
Hi, my name is Imanakia.
Hi guys, my name is Natasha.
And my name is Muhammad Arif. We are from Group 21, and we will be presenting Escalator Control System for Energy Efficiency with Emergency Stop. Escalators are a convenient way of transporting people between different levels. General escalators typically operate continuously at a speed regardless the amount of people using them. This constant operation raises concerns on the energy usage. At certain times, the escalator consumes an unnecessarily amount of energy despite the low number of people actually using the escalator. So this project aims to optimize the energy efficiency of an automated escalator with the integration of a PLC control system.
So the first problem statement is that conventional escalators runs continuously, which will technically lead to waste energy, and especially during off-peak hours. So the second problem statement is that conventional escalators lacks in quick emergency response, which will affect the safety risks during malfunctions. So this project proposes a PLC-based intelligent control system with two features, which is first one, the motion sensors for energy efficient operation, and the second feature is emergency stop function for quick response.
First objective, to integrate motion sensors to detect motion and activate or deactivate the escalator accordingly. Second, to reduce maintenance costs and mechanical wear. Third, to develop an intelligent control system using PLC. For design capabilities, first, motion sensors to detect user presence. Second, PLC control to ensure precise timing. Third, time delays prevent unnecessary restarts. Next, user-friendly reset to allow manual reactivation. Next, cost-effective and energy efficient to reduce power consumption and improve the system longevity. Last but not least, smart automation to enhance the operational efficiency.
So the first article, which is the Programmable Logic Controllers, Principles and Applications, this article tells us about why PLC is a good relay system compared to the old relay system and its main parts that has been used in PLC. So the second article is the evolution of programmable logic controllers in manufacturing. In this article, it tells us how PLC has improved over time. PLC, Programmable Logic Controllers, Principles and Application, but this time is more specific to our topic, which is how PLC technology is used to control escalators. In this article, we learn how PLC helps save energy in escalators, how emergency can be used, and also how sensors detect people that are coming to the escalators, which help the escalator to move, as well as how the escalator speeds up when someone is nearby.
The first symbol is a normally open input contact, or NO. This symbol is when the condition is true, then the contact is closed and the output logic flow is enabled. The second one is the normally closed input contact, NC. When this condition is true, then the contact is open and the output logic flow is blocked. The third one is the output coil. The input condition transitions from false to true, then the output is on for the time taken to do the PLC scan. The fourth one is timer delay on, TON. This is when the input condition is true, then the timer begins, and when the preset time has been reached, the output turns on. Next is timer delay off, so timer delay on, timer delay off. When the input condition is true, then the output turns on. If the input condition goes false, the timer begins, and when the preset time has been reached, the output turns off. And the last one is the PID controller, to control the process value. The process variable is measured from the primary element input, and the output is manipulated to maintain the process variable value at the set point input value. So this paper examines energy consumption patterns of intermittent operating escalators, highlighting significant energy savings during low passenger traffic. It presents data from long-term measurements of an escalator paired with a speed control and stop-and-go modes. The study concludes that power consumption profiles depends on the passenger flow, and that it identifies a potential energy reduction of up to 52% compared to continuously running escalators.
For the methodology, we want our escalators to conserve energy when there is no motion detected. Of course, there will be a time interval of 30 seconds and 60 seconds to maintain the efficiency. The crucial part of the system will be the emergency button or push stop button that will be used in the PLC circuit diagram that will immediately stop the whole system in case of any emergency. Now, let's break down the flowchart which visually represent this logic. The process begins when the system starts. The first check is whether the emergency button is pressed. If it is, the system immediately stops to ensure safety. If not, the system initiates a 30-second timer before checking for motion detection. If motion is detected, the escalator runs at full speed. However, if there is no movement for 30 seconds, the system reduces the motor speed, entering energy-saving mode. At this stage, a 60-second timer begins. During this period, if motion is detected, the escalator returns to full speed, but if no motion is detected for 60 seconds, the system completely stops the motor, conserving energy. At any point in this process, pressing the emergency button overrides all operations, stopping the escalator immediately until it is manually reset. This flowchart provides a structured approach to efficiency and safety, ensuring that the escalator only runs when necessary while integrating a fail-safe emergency stop. Thank you.
Now that you know about the working principle and the logic implemented in our PLC program through the sequence of events, I'll be presenting our PLC ladder logic design for an energy-efficient escalator control system. Let's go through the PLC ladder logic step by step. Let's say rung 1. The first rung contains the start button, stop button, and the motor coil. When the start button is pressed, the motor turns on, provided the stop button is not activated. The motor remains latched on due to a holding contact until a stop condition is met, which is when the stop button is on. In rung 2, once the motor is on, you can see that a 30-second on delay timer T30 is triggered. If motion is detected during this time, the escalator remains in full speed operation. However, if no motion is detected after 30 seconds, the next rung is activated. We'll wait for a few more seconds and we'll see what happens. Right, so now in rung 3, where if no motion is detected for 30 seconds, the system transitions to energy saving mode, which is the eco mode. This is achieved by switching from the full speed motor control to an energy efficient mode. Here, you can see it has been 30 seconds and there is no motion, so it went into the eco mode. Next, in rung 4, while in energy saving mode, a 60-second timer T60 starts counting. It has been 35 seconds here. So if motion is detected within this duration, the escalator returns to its normal speed. See? It returns to its normal speed. So if no motion is detected, the system will proceed to shut down the motor. We'll wait for around 50 seconds and we'll see what happens. So next, in rung 5, so once the 60-second timer elapses without motion detection, the motor is deactivated and turning off the escalator completely. You see? It turns green, and so the escalator is turned off completely. This ensures energy efficiency when the escalator is not in use. And of course, safety is a crucial factor in our design. If the emergency stop button is pressed at any time, the motor turns off immediately, and the system will remain disabled until manually reset. This will prevent any accidents and ensures the user safety. You see? All the motors are completely off.
Firstly, it reduces the electricity costs associated with continuous escalator operation. Traditional escalators consume a large amount of power, even when idle, whereas this system minimizes unnecessary energy consumption, making it more cost-effective. Additionally, by decreasing wear and tear on mechanical components, maintenance costs are reduced, and the escalator's lifespan is extended. The integration of an emergency stop also aligns with safety regulations, reducing liability risk for businesses operating in malls, airports, and public transport hubs. Overall, the results confirm that this PLC-based control system is an effective, energy-efficient, and safe solution for modern escalators. It optimizes energy use, improves system reliability, and enhances user safety, making it a practical innovation for commercial applications.
In conclusion, optimize energy usage. Motion-based operation reduce unnecessary power consumption. Second, to enhance safety. Emergency stop function ensure immediate hazard response. Third, cost-effective solution by lowered electricity and maintenance expenses. Last but not least, this project is ideal for modern infrastructure, which is suitable for commercial spaces and also transport hubs. So, recommendation for future work. First, adaptive speed control by adjust the speed dynamically based on foot traffic. Second, IoT and data analytics by collect usage data for predictive maintenance. Next, renewable energy integration by explore solar power or regenerative braking. Next, remote monitoring and control by develop mobile or web-based dashboards. Next, enhance AI-based safety by detect the faults before failures occur. Last but not least, user-friendly interface, touchscreen for maintenance and settings. So that's all from us, Group 21. Thank you.